Okay, in my last video, I looked at three interesting infinite series, three McLaurin series. The McLaurin series for e to the power of x, the McLaurin series for sine of x, and the McLaurin series for cosine of x. And we did a little bit of investigation around there. In this class, we're going to look at taking derivatives of these things, derivatives of this function, derivatives of sine of x, derivatives of cosine of x, using the McLaurin series to find the derivatives. Before we do, I'm just going to mention these special kind of functions that appear. So if I take, say, let's take a simple one, x to the power of 2 over 2 factorial, and I want to take the derivative of that function. Notice 2 factorial is a constant, so we can factor out the 1 over 2 factorial. Just take the derivative of x squared, which is 2x, and then factor your 2 factorial back in. That's 2 factorial, which is of course, just 2. 2 factorial and the 2 cancel out to leave me with x. And suppose I take the derivative of a similar function, x to the power of something, 3 in this case, divided by the factorial of 3. And again, on the bottom we have a constant, so we can factor that out. Just take the derivative of the top. 3x squared, and on the bottom we'll still have 3 factorial. Now 3 factorial can be written as 3 by 2 factorial. That's kind of the definition of what a factorial is. And the 3's here, you can see, will cancel. So what I get is x to the power of 2 over 2 factorial. And notice what's happened here is the degree on the x has dropped by 1 and the factorial has dropped by 1. Let's look at one more example before we generalize. Suppose I take the derivative with respect to x. So let's just pick any number. Suppose I said x to the power of 10 over 10 factorial. Again, 10 factorial on the bottom. That's a constant, so I'm going to factor that out. Just take the derivative of the top part, x to the power of 10. That's going to be 10 times x to the power of 9. And on the bottom, we'll have 10 factorial factored back in. 10 factorial is just 10 by 9 factorial. 10s will cancel. So we get x to the power of 9 over 9 factorial. And I'm hoping at this stage you can see what will happen. You know, let's formalize that, with a little rule here. If I take the derivative with respect to x of x to the power of any number divided by the factorial of that exponent. Well, again, if that's a constant, we can factor it out. N factorial. And n factorial, remember, is n just times n minus 1 factorial. And on the top, we'll use our power rule. That's n times x to the power of n minus 1. And what's going to happen every time is those n's will cancel to give me x to the power of n minus 1 over n minus 1 factorial. So what this is saying is if I have x raised to some power, and then on the bottom I have that same number, factorial, well then the derivative of that will be, the exponent will be decreased by 1 and the factorial will be decreased by 1. Okay? So let's look at using that in finding derivatives of these three kind of special functions. Standard derivatives, actually, they are listed in your tables, but I just want to go through why this is. So I take the derivative with respect to x of e to the power of x. Well, that's just the derivative with respect to x of this infinite series. Remember, e to the power of x is this infinite series. Because it's a series, it's just a sum of terms, and my sum and difference rule for derivatives say just take the derivative of each term individually. The derivative of the first term will be 0. So I'm not going to bother writing anything in there. Plus the derivative of x we know is 1. Plus, and this is one of these special functions we were just talking about of this type, x to the power of n over n factorial. We're just going to decrease the exponent by 1 and decrease the factorial by 1. So I'm going to get x to the power of 1 over 1 factorial, which is, of course, just x. Again, these are all this kind of function. Decrease the exponent by 1, x squared over 2 factorial. This one, decrease the exponent, we get x to the power of 3. Decrease the factorial, we get 3 factorial. And that's going to go on. And what I'm hoping you see is that is actually equal to e to the power of x. So derivative of e to the power of x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x power 4 over 4 factorial, etc. And that's an important standard derivative, that if I take the derivative with respect to x of e to the power of x, I will get e to the power of x. The e to the power of x is its own derivative. It's a very special property of that function, e to the power of x. Let's use the McLaurin series to take the derivative of sine of x. So we're taking the derivative with respect to x of, and I wonder, can you remember what the McLaurin series for sine of x was? You know, pause video, think if you can write it down. And let me write it in now. It's x minus x cubed over 3 factorial. Only the odd exponents are in there, and the signs alternate between negatives and positives. So next one will be the next odd exponent, 5. Next odd factorial, 5. Subtract now. Next odd exponent, 7. Next odd factorial, 7. Add now. Next odd exponent, 9. Next odd factorial, 9. And that goes on forever and ever. So if we take the derivative of this function, the derivative of x is 1. This is one of those special kinds of functions we spoke about at the start. And again, let me just bring it up here to remind you. To take the derivative of a function of this type, x power of n over n factorial, we're just going to decrease the exponent and decrease the factorial, each of them by 1. So this is going to become x power of 2 over 2 factorial. The derivative of the next term will be x to the power of 4 over 4 factorial. The derivative of the next term will be negative x to the power of 6 over 6 factorial. The derivative of the next term will be x to the power of 8 over 8 factorial, and so on. And what do we get there? Well, if we look back at our McLaurin series page, that is actually what cosine is. 1 minus x squared over 2 factorial plus x power 4 over 4 factorial, etc. This is actually equal to cosine of x. So the derivative with respect to x of sine of x is cosine of x. Okay, and let me look at the last function here. And, you know, again, I recommend pause the video, see if you can take the derivative of this, take the derivative with respect to x of cosine of x. It's going to be the derivative with respect to x of, can you pause the video, write out the McLaurin series, and then take the derivative? I'm going to go through it here. Well, we know that cosine of x is 1 minus x squared over 2 factorial plus x power of 4 over 4 factorial minus x power of 6 over 6 factorial plus x power of 8 over 8 factorial, and that pattern continues forever. It's an infinite series. And if I take the derivative of this series, it's a series, so it's sums and difference, or sum or difference rules. Let's just take the derivative of each term individually. The derivative of 1 with respect to x is 0. Any constant, derivative of any constant is always 0. And then we have a negative. And again, applying our rule here, we're going to decrease the exponent by 1. That's x power of 1 over 1 factorial, which is just x. So we get actually a negative x there as our first term. And then plus x power of 4 over 4 factorial. Well, the derivative, we're going to reduce the exponent by 1, x cubed, and reduce the factorial by 1, 3 factorial. Take the derivative of the next term. We get x power of 5 over 5 factorial. And again, just applying our rule that we developed at the start of class, x to the power of some number over that number factorial, decrease the exponent by 1, x to the power of 7, and decrease the factorial by 1, 7 factorial. And that goes on forever and ever. Now, let's just think about this. It's negative x plus x cubed. But if I factor out a negative 1 from this, it's actually factor out a negative 1 from the first term, it's going to be x. And then from the second term, it's going to be negative x cubed over 3 factorial. And then from the next term, it would be positive x to the power of 5 over 5 factorial. And then from the next term, it would be minus x to the power of 7 over 7 factorial. and so on, forever and ever. And what I'm hoping you're seeing at this stage is that that's -1 multiplied by this series. And this series was precisely what sine of x is. So the derivative of cosine of x is -sine of x. Okay, and those are 3 standard derivatives. These are all given in your formula and tables booklet. Let me just formalize that by writing it down. Write it down here. So let's get rid of this page. The derivative with respect to x of e to the power of x is e to the power of x. We've just proven it. The derivative of, with respect to x, of sine of x is cosine of x. We've just seen that using the McLaurin series. The derivative with respect to x of cosine of x is -sine of x. We've just proven it. Okay? These are all in your formula and tables booklets, along with other standard derivatives. Standard derivatives. They crop up all the time in our course. Get used to them. You should really know these by heart, but you'll get more familiar with them with practice. So that's why the derivative of each of these is what it is. Go through the video, make sure you can understand it. Again, try to prove that yourself. And then I'll look in our next lesson at taking derivatives of some trigonometric functions.